Water is a prerequisite for life. The first living organisms originated in the water environment. But what makes it unique? Water has a list of unusual properties, for example, unusually high melting and boiling points. Ice, the solid state of water, is lighter than liquid water, while solids are usually heavier than liquids. Recently, scientists have tried to explain the origin of these anomalies.
Water molecules are held together due to hydrogen bonds. A hydrogen bond in water occurs when an oxygen atom of one molecule is bonded to a hydrogen atom of another one. Due to these hydrogen bonds, a three-dimensional tetrahedral network is formed. But is all water tetrahedral? In 1892, a German physicist, Wilhelm Röntgen, proposed that water can be presented as a mixture of two liquids, a low-density one LDL and a high-density one HDL.
This hypothesis has been further developed into the two-state model, according to which
in LDL there is order due to hydrogen bonds, which limit the number of neighbor molecules and lead to low density. In HDL there is disorder because molecules are closely packed together, hydrogen bonds get broken, thus leading to higher density. As yet, HDL and LDL as pure liquids have been observed in the regime of supercooled water, the temperature of which is lower than 0 degrees Celsius and which nevertheless is liquid. Normal water is considered to be dominated by HDL, while the proportion of LDL is much smaller. This is a phase diagram which illustrates different states of water under changing conditions, temperature and pressure. Here you can see a region indicated by the yellow line where there is a significant proportion of LDL and hence the anomalies take place, and a sub-region indicated by the red line where temperature is higher than 0 degrees Celsius while pressure is fluctuating around 100,000 pascals. Such conditions are called standard. We live under these conditions. In 2018, scientists from the University of Tokyo ran a program which was a computer simulation of the two-state model. While tuning the proportion of LDL through different parameters, they found out that the more tetrahedral the structure of water is, the more anomalies water has.
So can the two-state model provide us with the explanation for the anomalous behavior of water?
Ice has a well-organized structure of molecules, fairly like LDL, while water is dominated by HDL. If LDL has lower density than HDL, it is lighter, right? So ice is lighter than water and floats on its surface. Otherwise, rivers and lakes would freeze all the way to the bottom in the wintertime, and there would be no underwater life.
This is an example of significance of the water anomalies. It's also important to remember that were it not for the standard conditions like pressure being much higher than 100,000 pascals, there would be almost no LDL in water, no anomalies, and thus no life.
That's why this anomalous part of our diagram is a vitally important zone.
Just think of the happy coincidence that there is water on a planet where such standard conditions are taken for granted. Today, scientists are looking for water and various life forms on other planets. Studying water and its unique properties can tell us more about this amazing substance and the origin of life.